Hello there. Welcome to this quiet corner of curiosity. Tonight, we aren't looking out at the stars for answers. We're going to look down, deep beneath our own feet, and ask something unsettling. To begin, just imagine this. Geologists, drilling a deep sediment core from the quiet floor of the Antarctic Ocean, pull up a sample. They date one layer using the reliable decay of isotopes to 100 million years ago, the time of the dinosaurs. But inside this ancient, compacted mud, they find something impossible. Not fossils, not volcanic ash, but microscopic, synthetic polymers. Microplastics. What would such a discovery imply? It would mean that everything we know about our planet's history is incomplete. It would suggest that the story we tell ourselves, a story of one linear progression from single cells to us, is wrong. It would mean our industrial, plastic-producing civilization is not the first, but merely the latest. It would mean we have been living on the ruins of a world we never even knew existed. Now, to be clear, this discovery has not happened. That core sample does not exist. But the thought experiment itself is powerful, and it is no longer confined to late-night speculation. We spend vast resources scanning the cosmos, listening for signals from distant stars, searching for any sign that we are not alone in the universe. But what if we've been neglecting the most obvious place to look? What if we failed to check beneath our own feet? What if, long before human hands chipped the first stone tool, long before the first pyramids pointed at the stars, another civilization rose, flourished, and fell, right here on Earth? This isn't a conversation about mythical lost continents like Atlantis or ancient alien tourists. This is a serious, methodical scientific question, posed not by fringe theorists, but by career scientists at the highest levels. It is a question that asks, fundamentally, if an industrial civilization like ours had existed in the deep past, could we even tell? Or would the slow, relentless grinding of the planet's geology, the subduction of plates, the erosion of mountains, the constant recycling of the crust have erased every trace? It's a thought experiment with a formal name born from a 2018 paper by leading climate scientists. It is known as the Silurian Hypothesis, and it forces us to confront the most humbling question imaginable. Are we the first? To even begin to ask this question, we must first recalibrate our sense of time. When we speak of ancient history, we are typically thinking of Egypt, of Mesopotamia, of the first inscriptions on clay tablets. This is a timescale of thousands of years. Even the entire history of our species, Homo sapiens, is only a few 100,000 years old. This feels immense to us. It fills our libraries and museums. But in the language of the planet, it is not even a full sentence. It is a single, fleeting breath. The Earth itself is 4.5 billion years old. The story of our planet is not written in the ink of human history. It is written in rock, in heat, and in pressure. This is deep time, and the first rule of deep time is that the planet is not a passive archive. It is not a library that carefully preserves every book. The planet is a relentless, active, and profoundly destructive recycling machine. We live on the thin, fragile outer crust, which is fractured into massive tectonic plates. These plates are in constant, slow motion, floating on a sea of molten mantle. Where they collide, mountains rise. Where they pull apart, new oceans are born. And, most importantly, where one plate slides beneath another, a process called subduction, the entire surface of the planet is dragged down, crushed, and melted back into magma. This is the planet's ultimate act of erasure. The entire floor of the world's oceans is recycled this way. The average age of the ocean floor is only about 180 million years. This means that any part of the seabed older than that, anything from the time of the early dinosaurs, for example, is already gone. It has been pulled back into the Earth, its history, its fossils, its layers, all of it melted and reformed. The planet systematically destroys its own memory. On land, the process is different, but just as effective. Erosion by wind, rain, and ice grinds mountains down to sand. Rivers carry this sand to the sea, burying landscapes under kilometers of new sediment. Glaciers scrape continents clean, down to the bedrock. What we see on the surface is not a permanent record. It is merely the current page, and it is already being torn out. This is the staggering reality that confronts us. The survival of any fossil, any trace from the deep past, is a profound exception. It is a statistical miracle. It requires an organism to die in the exact right place, a quiet lakebed, a tar pit, an ash fall be buried instantly, escape being crushed or melted for millions of years, and then, by chance, be pushed back to the surface where we can find it. The vast majority of all life that has ever existed has vanished without a single trace. If this is true for bones and shells, imagine the challenge for something far more fragile. A skyscraper, a circuit board, a library. Against the timescale of deep time, these things are as temporary as footprints in the sand, waiting for the tide. This profound problem of erasure is precisely what led to the formal hypothesis. This question didn't emerge from the fog of pseudoscience or conspiracy. It was born from a paper published in 2018 Inches, the International Journal of Astrobiology. Its authors were not fringe theorists. They were two highly respected, mainstream scientists. The first was Gavin Schmidt, the director of the NASA Goddard Institute for Space Studies, one of the world's leading climate scientists. The second was Adam Frank, an astrophysicist from the University of Rochester. Their motivation was not to find a lost civilization on Earth. Their motivation was, in fact, rooted in the stars. As an astrophysicist, Adam Frank is part of the search for life on other planets. This search has recently evolved from looking for life to looking for technosignatures, the global, chemical, or atmospheric fingerprints that a technology-using civilization might leave behind. But this raises an immediate problem. We have only one example of such a civilization, our own, and we don't even know what our ultimate geological fingerprint will be. Schmidt and Frank realized that before we could claim to find a civilization on a distant exoplanet, we had to answer a more basic question. What does an industrial civilization look like to a planet? What is the generic, long-term, geological signature of this kind of activity? The only way to test this was to use Earth itself. Their paper was a thought experiment. It asks, if a civilization like ours had existed millions of years ago, what would be left of it? Would any signal survive the great geological erasure machine? And if it did, what would it be? They called it the Silurian Hypothesis, a playful nod to the classic Doctor Who television series, which featured an advanced reptilian species, the Silurians, who lived on Earth millions of years before humanity evolved. The name was cheeky, but the science was serious. The paper was not an argument for the existence of the Silurians. It was a methodical investigation into the methods of planetary science. It forces us to define our own time, the Anthropocene, not as a human story, but as a set of physical and chemical signals. By understanding what we are doing to the planet today, we can create a template. We can then use that template to scan Earth's own deep history for any ghost signals, any anomalies in the rock record that don't fit a natural pattern, and that might, just might, look like ours. To hunt for the ghost of a lost civilization, we must first understand the ghost we are currently creating. We need to become planetary archaeologists of our own time. This is the central method of the Silurian hypothesis. Using our present, the Anthropocene, as the laboratory. The Anthropocene is the proposed name for our current geological epoch, an age defined not by a shift in ice or volcanoes, but by the global, transformative impact of a single species, us. For the first time, we can catalogue, in real time, the signals an industrial civilization imprints upon its planet. These signals are the template, the fingerprint we are searching for in the deep past. This fingerprint is not one thing, but a suite of interlocking markers. The first and most profound is the change to the global carbon cycle. Our civilization runs on fossil fuels, coal, oil, and natural gas. These fuels are the buried remains of ancient life, life that preferentially absorbed a lighter isotope of carbon, carbon-12. When we burn these fuels, we are flooding the atmosphere with this ancient C12-rich carbon at a rate hundreds of times faster than any known natural release. This flood changes the C12 to C13 isotope ratio in the entire atmosphere and all the world's oceans. This signature is being inhaled by plankton, absorbed by corals, and locked into sediments right now. It is a global, unambiguous, and powerful signal. The second marker is the advent of purely synthetic materials. Our world is filled with molecules that nature never invented. Plastics are the most famous example polymers of such complex and durable structure that many microbes do not yet know how to consume them. We are producing hundreds of millions of tons of this material every year, and it is washing into the oceans, settling in the deepest trenches, and even being carried by wind to the most remote polar ice caps. But plastics are not alone. We have created persistent organic pollutants, POPs, industrial chemicals like PCBs, and countless other novel compounds. These are technofossils. Their presence in a layer of sediment is a definitive sign of an unnatural industrial process. The third marker is a sudden, sharp spike of radioactivity. The brief period of above-ground nuclear weapons testing in the mid-20th century left an indelible mark. It scattered specific, synthetic radionuclides, isotopes like cesium-137 and plutonium-239 across the entire planet. This radioactive fallout settled everywhere, creating a razor-thin, global layer that will serve as a definitive golden spike for future geologists, marking the precise moment our species gained the power of atomic fission. Finally, there is the signal of nitrogen. To feed our population of billions, we effectively hijacked the planet's nitrogen cycle. The Haber-Bosch process, invented in the early 20th century, allows us to pull inert nitrogen gas from the air and turn it into ammonia for fertilizer on an industrial scale. This has fundamentally altered the chemistry of our planet's soils and, crucially, the runoff into its oceans. This surge of artificial nitrogen, with its own distinct isotopic signature, is being recorded in marine sediments, right alongside the carbon. A carbon spike, a synthetic molecule, a radioactive pulse, and a nitrogen surge. This is the complex, four-part signature of the Anthropocene. This is the ghost we are leaving behind. Now, we take this fresh, four-part fingerprint and subject it to the ultimate test of time. Let us perform the thought experiment at the heart of the hypothesis. We vanish tomorrow. What happens to this signature after 100 million years? What survives the great geological erasure machine? We must first clear away the debris of our own vanity. Our cities, our monuments, our great works of art and engineering, they are the first to go. Steel, the backbone of our world, is an inherently unstable material. It is a refined iron that desperately wants to return to its natural state. Rust. In a few centuries, our bridges and skyscrapers will have collapsed. Concrete, our other miracle material, is stronger, but it is not eternal. It cracks, water seeps in, ice expands, and plant roots pry it apart. Over millennia, it will be weathered, broken, and ground down, eventually becoming little more than an unusual, calcium-rich layer in the soil. Our roads will be buried, our houses will decay into organic dust. What about our artifacts? Our cars, our computers, our libraries? The metals will oxidize, turning back into mineral ores that might appear as strange, localized concentrations, but would be difficult to prove as artificial. Glass, which we think of as permanent, is a non-crystalline solid. Over geological time, it is unstable and will devitrify, slowly recrystallizing back into quartz-like minerals, blending into the surrounding rock. Even our bones are unlikely to survive. Fossilization, remember, is a profound exception, not the rule. The vast majority of our 8 billion bodies will decompose and be recycled, leaving no trace. After 1 million years, almost every physical, structural, and monumental trace of our global civilization would be gone. But what about the ghosts? What about the chemical signals? This is where the story changes. The great carbon spike, that massive injection of C12, that survives. It would be locked firmly into the sedimentary rock layers formed from that time. A future geologist drilling a core sample would see a sharp, violent anomaly in the carbon isotope ratio, a line of ink in the planet's logbook that screams something happened. What of the plastics, the technofossils? This is a stronger candidate than one might think. While plastics on the surface break down, plastics that are buried in anaerobic sediment, oxygen-free mud at the bottom of the ocean, are in a perfect preservation environment. They might not survive as bottles or bags, but their long-chain, complex, synthetic molecules would persist. They would degrade, slowly, into other strange organic compounds that have no natural origin. A future scientist performing a chemical analysis of that sediment layer would find molecules that simply do not belong right next to the carbon spike. The radioactive signal? This one is more fragile. Most of the isotopes from weapons testing, like cesium-137, have half-lives of only decades. After 1,000,000 years, let alone 100 million, they would have decayed into nothing. However, some scientists suggest that longer-lived byproducts, like iodine-129 or traces of plutonium-244, might persist as a faint, anomalous trace, though it would be incredibly difficult to detect. And finally, the nitrogen signal. Like carbon, this is an isotopic signature locked into the chemistry of the ocean sediments. A future geologist would see that in the very same layer as the carbon anomaly, the nitrogen cycle also went haywire. The conclusion would be inescapable. Our legacy is not our buildings. Our legacy is not our statues. Our true, enduring, 100 million year legacy is our waste. Our tombstone is a single, thin layer of rock, perhaps only millimeters thick, defined by a sudden chemical scream, a spike in carbon, an echo of nitrogen, and the molecular ghosts of a synthetic world. This is the template. This is the signal that Schmidt and Frank proposed we search for. Let us look closer at these markers, for they are the alphabet of this new geological language. The first and most powerful letter is written in carbon. Carbon is the spine of all known life, but not all carbon is created equal. The universe provides it in several stable forms, or isotopes. The two most important are carbon-12 and carbon-13. They behave almost identically, but carbon-13 carries an extra neutron, making it just slightly heavier. Life, in its relentless quest for efficiency, finds it easier and faster to metabolize the lighter carbon-12. From the smallest plankton to the largest tree, life selectively filters the carbon it consumes, becoming enriched in C12. For billions of years, this process has been in balance. Trillions of these C12-rich organisms have lived, died, and been buried. Their organic matter slowly compressing under pressure and heat to become coal, oil, and natural gas. These are the fossil fuel's vast, buried reservoirs of ancient, light carbon. For all of planetary history, this carbon was locked away, sequestered deep underground, removed from the active cycle. Until now, our industrial civilization runs by reversing this process. We have become a geological force, digging up this ancient C12-rich material at a furious pace and setting it on fire. We are releasing hundreds of millions of years of buried carbon back into the atmosphere in the span of just 2 centuries. The result is that we are fundamentally changing the isotopic signature of the entire planet. We are flooding the system with so much light carbon that the natural C12-C13 ratio is being diluted. The entire atmosphere is, measurably, becoming isotopically lighter. This is not a subtle or localized signal. Carbon dioxide mixes through the global atmosphere in a matter of years. The atmosphere, in turn, exchanges this carbon with the surface of the oceans. The microscopic plankton and corals living in that water build their shells from calcium carbonate, using the carbon available to them. And in doing so, they are building their shells out of our emissions. When these organisms die, they sink. Year after year, millennium after millennium, their tiny shells rain down, creating vast layers of sediment on the ocean floor. This sediment, which will one day become shale and limestone, is trapping a perfect, high-fidelity, permanent record of our industrial signature. A future geologist, drilling a core sample from that rock, would see a sudden, violent, and unprecedented swing in the carbon ratio. A spike that points unambiguously to a massive release of ancient, buried organic matter. A signature that nature, on its own, does not produce at this speed. The carbon spike is a signal of process. It shows a civilization doing something. The next marker is a signal of product. It is the physical residue of a civilization that is making things. These are the technofossils. While our monuments of steel and concrete will crumble, our chemical creations are a different story. The 20th century was defined by our mastery over polymers. We learned to string together carbon, hydrogen, and other elements into long, complex chains that nature had never invented. Plastics, polyethylene, polypropylene, polyvinyl chloride. These materials are revolutionary precisely because they are alien. Life has had billions of years to evolve enzymes and bacteria capable of breaking down natural polymers like wood, protein, and fiber. It has had less than a century to deal with a plastic bottle. As a result, these materials do not biodegrade in any meaningful way. When exposed to sunlight and air, they merely break down, not break apart. UV radiation shatters them into smaller and smaller fragments, from macroplastics to microplastics to nanoplastics. These synthetic particles are now everywhere. They are in the air we breathe, the food we eat, and, most importantly, the oceans we pollute. They are being carried by currents to every corner of the globe, from the Arctic ice cap to the bottom of the Marianas Trench, and just like the shells of plankton, they are raining down onto the seafloor and being buried in the sediment. This is the key to their persistence. In the dark, cold, oxygen-free mud of the deep ocean, the primary forces of degradation, sunlight, and oxidation are absent. Here, these unnatural molecules are in a state of perfect preservation. 100 million years from now, a future scientist will not find an intact plastic bag, but by analyzing that thin layer of Anthropocene sediment, the same layer with the carbon spike, they will find something else. Using tools like a mass spectrometer, they will find complex, synthetic, long-chain hydrocarbons molecules that simply have no business being there. This signal is not just compelling, it is virtually foolproof. While a massive natural release of methane could, in theory, mimic some aspects of the carbon signal, there is no natural process that manufactures polyvinyl chloride, and this signature is not limited to plastics. We have synthesized tens of thousands of other novel compounds. Persistent organic pollutants, POPs, like PCBs, which were used for decades as industrial coolants, complex pesticides, and countless other industrial chemicals. These, too, are washing into the sea and being locked into the same sedimentary layer. This suite of unnatural molecules, the technofossil signature, is perhaps the most definitive trace we will leave. It is a chemical calling card. It is marker number 2, an unambiguous fingerprint that says, "We were here, and we changed the very stuff of the world." The chemical and molecular signals are markers of what an industrial civilization produces, but there is another, darker signal, written in the language of biology itself. This is the marker of what such a civilization displaces. This is the signal of extinction. Life on Earth has been punctuated by 5 great mass extinction events, moments in deep time when the planet's biodiversity collapsed catastrophically, usually from global-scale natural disasters like supervolcanoes or asteroid impacts. According to an overwhelming scientific consensus, we are now living through and actively causing the 6th, our rapid expansion, our transformation of landscapes, our pollution, and the climate change we are driving have triggered a biological crisis. Species are vanishing at a rate estimated to be 1,000 times the natural background rate. This is not a slow, gentle decline. It is an abrupt, violent termination of entire evolutionary lineages. And this, too, will leave an unambiguous signal in the geological record. How? The fossil record, as incomplete as it is excellent at recording disappearances. A future paleontologist examining the rock layers from our epoch would see a sudden, catastrophic drop in biodiversity. They would see abundant, diverse, large animal species, the megafauna, like elephants, tigers, rhinos, and whales thriving in the layers just before the Anthropocene boundary. Then, in the layers immediately after, they would be gone. Vanished. This biological decimation, happening in perfect synchrony with the chemical spikes, becomes a powerful corroborating line of evidence. It paints a picture of a planet under extreme stress, of a new and dominant global force so disruptive that it triggered a planetary-scale biological collapse. This is marker number 3. Finally, we come to the 4th marker, which is perhaps the most subtle, but also the most intimate. It is the signature of how an industrial civilization chooses to feed itself. For all of human history, our population was limited by the available nitrogen in the soil, the essential nutrient for all agriculture. That all changed in the early 20th century with the invention of the Haber-Bosch process. This was the chemical miracle that allowed us to pull inert nitrogen gas directly from the atmosphere and fix it into ammonia, creating a near limitless supply of synthetic fertilizer. This invention is the reason our population was able to explode from 6 billion to over 8 billion in just 1 century. We are, in a very real sense, a species grown from artificial nitrogen, but this act of feeding ourselves has, like burning fossil fuels, hijacked a fundamental planetary cycle. We are now fixing more nitrogen synthetically than all natural processes on Earth combined. This massive flood of reactive nitrogen doesn't just stay on the farms. It is washed by rain into rivers, and from rivers into the sea. Just like carbon, this industrial nitrogen has its own unique isotopic signature, one that is measurably different from naturally fixed nitrogen. And just like carbon, this signature is being absorbed by marine organisms and, crucially, locked into the ocean sediments. A future geologist, analysing the exact same layer that contains the carbon spike, the technofossils, and the extinction signal, would also find a bizarre and massive anomaly in the nitrogen isotopes. They would see, chemically, the signature of our global agricultural system. And this agriculture leaves a second, physical trace. To create these vast farms, we have clear-cut continents. This massive deforestation, coupled with intensive ploughing, has destabilized the planet's topsoil. The result is a colossal increase in soil erosion. For the last several thousand years, rivers have been bleeding mud and silt into the oceans at an unnatural rate, a physical flood of sediment that is building up in deltas and on continental shelves. This, too, forms a distinct layer. It is a physical blanket of eroded land, laid down at the precise moment the planet's chemistry was being rewritten. This is the complete, 4-part fingerprint of the Anthropocene. It is not one signal, but a complex, interlocking harmony of failure and success. It is the carbon signature of our energy, the synthetic signature of our materials, the extinction signature of our expansion, and the nitrogen and silt signature of our food. They are all happening at the same time, all pointing to a single, global, technological cause. This is the specific, durable, and complex signal that a civilization like ours will leave behind. This is the template. This is the ghost that we must now search for in the deep geological past. So we are now equipped. We are no longer wandering through the archives of deep time, shining a light randomly into the dark, looking for vague shapes. We have a specific template. We have a face. We are searching for a complex, 4-part signal, a rapid C1, 2-rich carbon spike, a corresponding layer of unnatural synthetic molecules, a sudden mass extinction, and a simultaneous disruption of the nitrogen cycle. This is the specific fingerprint of an industrial civilization, and so the search begins. We take this template and we scan the geological record. We look at the data from ice cores, at ocean sediment layers, at the chemical composition of ancient rocks. We are no longer looking for a single out-of-place artifact. We are looking for a planet-wide chemical event. We are looking for our own reflection in the deep mirror of the past. As we scan back through time, past the ice ages, past the rise of our own genus, we move into the deep Cenozoic era. And as we do, our scanners stop. A signal flares up. It is not a perfect match, but it is alarmingly, shockingly close. It is the most prominent, rapid, and globally disruptive climate event in the entire 5 million year history since the dinosaurs vanished. It is an event that, for decades, has puzzled geologists and paleoclimatologists. It happened 56 million years ago, at the boundary between the Paleocene and the Eocene epochs. It is known as the Paleocene-Eocene thermal maximum, the PETM, and it is, for all intents and purposes, the greatest imposter in the geological record. It is the perfect candidate for a Silurian ghost. Let's look at the evidence, at what the rock layers from 56 million years ago actually show. The story they tell is terrifyingly familiar. It begins with carbon. The sediment cores show a sudden, massive injection of isotopically light, C1, 2-rich carbon, into the global atmosphere. The source is still debated, but the chemical signature is identical in type to the one we are creating today by burning fossil fuels. The amount was staggering thousands of gigatons, perhaps as much as we would release if we burned all known fossil fuel reserves on the planet. The planetary consequences were immediate and catastrophic. This flood of greenhouse gas triggered a runaway global warming. The data shows that the Earth's average temperature rocketed upward by 5 to 8 degrees Celsius. The poles, previously forested, became subtropical. Alligators and palm trees thrived in what is now the Arctic. It was a hothouse world, transformed in a geological instant. This, in turn, triggered the next marker. All that carbon in the atmosphere didn't stay there. It was absorbed by the oceans, forming carbonic acid. The result was a rapid, global-scale ocean acidification. The seas became corrosive. We see this preserved in the rock. In many ocean basins, the layers of white chalk, formed from the shells of countless tiny marine organisms, abruptly stop. They are replaced by a dark, red clay. This clay layer represents a long period where the ocean water was so acidic that it dissolved the shells of these creatures as they died. Before they could even be preserved, their fossils simply vanished from the record. This acidification, combined with the extreme heat, led directly to the next marker, a mass extinction. While it was not one of the big five, it was a devastating biological event, particularly in the deep oceans, where over 50% of some single-celled organisms went extinct. The entire biological architecture of the planet was violently rewritten. The parallels are almost too perfect. A massive C12 rich carbon spike, rapid global warming, global ocean acidification, a mass extinction event. It matches 3 of our 4 primary markers with stunning precision. It is the exact same cascade of planetary failure that we are currently initiating today. It looks, for all the world, like a civilization hit an industrial tipping point, released all of its buried carbon, and pushed its biosphere into a state of collapse. It is a terrifying echo. It is a thin, dark line of rock that seems to scream a warning at us across 56 million years. This event is so similar to our present day that it is now studied by scientists, not as a geological curiosity, but as the single best analogue for the future we are creating. But for the Silurian hypothesis, it raises a far more profound question. Or is it the original? Is this the signal? Did Schmidt and Frank, in their thought experiment, accidentally find the very thing they were proposing? Is the PETM the tombstone of a real, industrial civilization that rose, burned, and fell 56 million years before we ever existed? This is where the rigor of true science separates itself from mere speculation. The PETM is a tantalizing candidate, an imposter so perfect it demands investigation, and this is exactly what Schmidt and Frank did in their original 2018 paper. They did not propose the hypothesis and leave this massive contradiction unresolved. They addressed it directly, head-on, in an attempt to falsify their own idea. This is what makes their work a robust scientific inquiry, not a declaration of belief. And when they compared the PETM to the Anthropocene, they found that the imposter, while good, failed 3 critical tests. The first, and most important, is the test of rate. The PETM was fast, shockingly so for geologists, but the data shows its massive carbon release was spread out over a period of at least 5,000 years. This, to a planet, is a sudden fever, but to us, it is a slow, relentless burn. Our own carbon release, by contrast, is a vertical spike. We have achieved in 2 centuries what the PETM took millennia to accomplish. This difference in timescale is crucial. A natural process, such as a vast, sustained series of volcanic eruptions in the North Atlantic, or the slow melting of deep-sea methane. Clathrates, frozen methane bubbles, due to shifting ocean currents, could plausibly release carbon over a 5,000-year period. But it is very difficult to imagine a natural process that releases carbon at the blistering, exponential pace of an industrial civilization. The PETM's signal is a very steep slope. Ours is a vertical line. They are not the same. The second test is the chemical fingerprint itself. While the PETM carbon was light, many datasets suggest it was even lighter than the carbon from burning fossil fuels. This points away from ancient forests, coal and plankton, oil, and points toward a methane-based source. As methane produced by microbes is extremely rich in carbon-1,2. The chemistry, while similar, does not perfectly match our specific brand of pollution, but the third test is the killer. It is the test of corroboration. A civilization's fingerprint is not one signal, it is a complex, four-part signature. The PETM has the carbon spike and the mass extinction. But where are the other markers? Where are the technofossils? Where is the layer of 5-6 million year old plastic? Where are the synthetic polymers, the PCBs, the industrial chemicals? Geologists have been studying the PETM boundary layer for decades, in minute detail, and no one has ever found a single, unambiguous synthetic molecule. There is no technofossil record. There is no nitrogen anomaly that perfectly matches our fertilizer signature. The PETM, in the end, is only a partial match. It is a ghost, but it is not our ghost. It is the ghost of a massive natural catastrophe, a warning from the planet itself, but not, it seems, the tombstone of a lost industrial predecessor. So, does this end the search? If the most prominent, most likely candidate in 65 million years is a false positive, does this mean the hypothesis is dead? Schmidt and Frank argue the exact opposite. This discovery doesn't end the search, it refines it. It teaches us what not to look for. The PETM was a massive, planet-altering event, but it was also slow and, in the end, chemically clean of industrial byproducts. This allows us to sharpen our tools. Perhaps we were looking for the wrong thing. We were looking for a signal as big as, or bigger than, our own. But what if a prior industrial civilization was less? What if it lasted for only 20,000 years instead of our potential 200,000? What if it collapsed, either by war, pandemic, or climate change, before it managed to burn all of its planet's fossil fuel reserves? Such a civilization would not create a massive disruption on the scale of the PETM. It would create a much smaller, faster, and dirtier signal. And this is where the hypothesis becomes truly fascinating. The geological record, particularly in the last 100 million years, is not just a smooth line with one big spike. It is full of smaller, briefer, and stranger climate events. Geologists call them hyperthermals. These are dozens of smaller, minor blips in the carbon and temperature record, little planetary fevers that lasted for just a few thousand years and are often overlooked, dismissed as geological noise, or filed away as unexplained data anomalies. The paper by Schmidt and Frank is, in effect, a powerful call to action. It is asking their colleagues in geology and paleoclimatology to go back to their data, to pull those old, uninteresting core samples out of storage, to look at those strange, minor blips in the record with a completely new set of eyes. Don't just dismiss that anomaly as noise. Analyze its rate. Was it faster than the PETM? Did it happen in a few centuries rather than millennia? And most importantly, run the test. Take those strange, thin, dark layers of rock and put them in a mass spectrometer. Are there any unusual, non-natural molecules? Are there strange metallic concentrations that don't match the surrounding geology? Is there a corresponding tiny drop in biodiversity in the same layer? The Silurian Hypothesis doesn't claim we've found anything. It provides a new toolkit for looking. It turns a wild speculation into a testable, methodical research program. It suggests that the evidence might not be a giant, obvious monument, but a subtle, missed signal hidden in the static. The question is no longer a vague "did they exist?", but a precise, scientific, can we find a complete, multi-part, industrial waste signature in any sedimentary layer from the last 500 million years? So far, the answer is no. But we have only just learned what to look for, and the planet's silent archive is vast, with so many pages still unread. At this point, the curious mind might raise an objection. But wait, it might ask, why are we searching for subtle chemical blips when we've already found things? What about the stories that bubble up from the fringes of archaeology, the artifacts that seem impossibly old? These are the so-called out-of-place artifacts, or UPARTs. They are the objects that seem to defy the known timeline, a metal hammer, like the London hammer, found embedded in Cretaceous-era rock. Grooved, metallic-looking orbs found in 2.8 billion-year-old deposits in South Africa. Stories of ancient, perfectly machined screws or spark plugs found in lumps of coal. These are the pieces of evidence that popular culture seizes upon. They are tangible, they are photogenic, and they are mysterious. Yet, They are not the evidence that Schmidt and Frank, or any other serious scientist, is looking for. And the reason why is the most important concept in all of geology: context. Science, particularly geology, is not the study of things, it is the study of systems. The geological record is not a treasure chest of objects. It is a library of layers, or strata. The single most important piece of information about an object is not what it is, but where it was, and in what layer it was found. Without this context, an object is meaningless. And every single famous oopart has failed the test of context. The London hammer was not found in Cretaceous rock. It was a 19th century hammer that had fallen into a crevice, where minerals in solution then formed a concretion around it, making the stone new, but the context modern. The Klerksdorp spheres are not machined. They are a well understood, entirely natural geological formation known as mineral concretions, which can, by chance, form in near-perfect spheres. And even if a single, inexplicable tool were found, what would it prove? It is mines, factories, supply chains, cities, and waste. The true, unambiguous signal of an industrial civilization must be global. A single misplaced artifact will always be dismissed, and rightly so, as contamination, intrusion, a hoax, or a misidentified natural object. But a global chemical spike, a synthetic molecule that appears in sediments in Antarctica, the Gobi Desert, and the floor of the Atlantic Ocean in the exact same time layer, that is not contamination. That is a planetary event. That is evidence. The search for ooparts is a search for a needle. The Silurian Hypothesis is a search for the signature of the entire haystack. This distinction, however, reveals the hypothesis's single greatest blind spot. It is a flaw, an assumption, so vast that it could hide an entire history of intelligence on our planet. The Silurian Hypothesis, as defined by Schmidt and Frank, is not a search for intelligence. It is a search for industrialization. It is a search for a civilization that followed our specific, dirty, and destructive path. It is a search for a society that, like us, discovered fossil fuels and burned them, that invented synthetic polymers and discarded them, that built a global agricultural machine and poisoned its own nitrogen cycle. The entire hypothesis is a mirror. It is designed, from the ground up, to find only one thing: a reflection of ourselves. But what if this is not the only path? What if intelligence does not inevitably lead to heavy industry? What if a species achieved profound complexity, self-awareness, philosophy, art, and language, but never built a steam engine? Imagine an aquatic civilization, perhaps descended from cephalopods, whose entire world was the ocean. They might develop a complex language of light and color, build cities from grown coral, and map the ocean currents, all without ever striking a match or smelting a single piece of iron. They would leave no carbon spike, no technofossils. They would be biologically advanced, but geologically silent. Or imagine a civilization that did reach an industrial phase. Perhaps, 500 million years ago, they built their first factories, saw the first smog, and measured the first change in their oceans. And then, with a wisdom we have not yet managed, they stopped. They dismantled their industrial machine, embraced sustainability, and perhaps built a civilization based on low-impact biotechnology or some other form of energy that lived in balance with the planet. They might have lived this way for 1 million or even 10 million years. A long, quiet, stable period of advanced consciousness. When they finally died out, what would they leave? Nothing. Their Anthropocene would be a tiny, almost invisible blip, easily missed, and their long, successful period of balance would leave no trace at all. This is the profound, humbling, and perhaps tragic limit of our search. We are searching for the scar. We are looking for the planetary signature of failure, the signature of a civilization that lost control, that burned its inheritance, and that poisoned its own biosphere. A civilization that was truly successful, one that was wise, sustainable, and lived in harmony with its planet, would be, by its very nature, invisible to geology. They would leave no industrial waste. They would trigger no mass extinction. They would leave the rock record as clean as they found it. We might be searching only for the loud civilizations, the ones that, like us, made a mess, The real great silence might not be the absence of life in the cosmos, but the geological silence of a wise civilization that we have no idea how to look for. There is yet one final, crushing filter. It is the single most powerful constraint on this entire hypothesis. A geological time limit that makes all other forms of erasure seem gentle by comparison. It is the planet's own built-in mechanism for destroying its past. The recycling of the ocean floor. We live on a crust of tectonic plates. These plates are not static. They are born, they travel, and they die. In the middle of our great oceans, at mid-ocean ridges, magma wells up from the mantle to create new, fresh crust. This crust spreads outward, like a slow-motion conveyor belt, carrying the continents with it. But the Earth is a finite sphere. For new crust to be born, old crust must die. And it does. At the edges of continents, in the deep ocean trenches, this older, colder, denser seafloor is forced to dive back down into the Earth's mantle. This is subduction. When this crust subducts, it is not buried. It is destroyed. It is superheated, crushed, and melted. Its materials reabsorbed into the planet's molten interior to one day be reborn as new magma, perhaps in a volcano, 100 million years later. This is the planet's ultimate recycling program, and it is relentless. This entire cycle, from birth to destruction, takes, on average, about 180 to 200 million years. What this means is that today, there is almost no piece of ocean floor on the entire planet that is older than the early Jurassic period. Everything older than that, every trace of the Triassic, the Permian, the Carboniferous, the Devonian, the Silurian itself, is gone. It has been physically, completely, and irrevocably melted. Now, consider the implication. Civilizations, as we understand them, are drawn to water. We build on coastlines. We build ports for trade, cities by river deltas for agriculture, and factories by the sea for cooling and waste. It is highly probable that any other industrial civilization would do the same. If such a civilization existed 300 million years ago, in the Carboniferous period, and built its shining capital cities along its coastlines, not just eroded, not just buried. They, and the very crust they sat upon, have been plunged into the mantle and turned back into magma. This sets a hard time limit on our search. Continental crust, being lighter and thicker, does not subduct. It survives for billions of years, but it is not a pristine record. For hundreds of millions of years, it is scoured by ice, washed by rain, and buried under kilometers of new sediment. Any civilization on a continent would be almost impossible to find. But any civilization on the coast, or on the 70% of the planet's surface that is ocean floor, is subject to a 200 million year death sentence. This vastly narrows the Goldilocks search window for any recoverable industrial waste signal to, realistically, the last 200 million years. The planet itself has burned the older library books. This, then, brings us to the true conclusion. After all this, after the search for signals, the debunking of imposters, the limitations of non-industrial intelligence, and the final, crushing erasure by plate tectonics, what is the point? If the search is this difficult, this constrained, if the evidence is so likely to be gone forever, why did two of the world's top scientists bother to ask the question at all? This is the final and most important part of the story. The Silurian Hypothesis was never truly about finding intelligent reptiles. It was never about proving a lost world. It was, and is, a mirror. It is a profound philosophical tool for reframing our own existence. For all our history, we have seen ourselves through the lens of human time. We see wars, empires, art, and ideologies. We see ourselves as the protagonists of a grand narrative. The Silurian Hypothesis forces us, for the first time, to see ourselves as the planet sees us. It forces us to see our civilization not as a story, but as a geological event. We are not the pinnacle of 4.5 billion years of evolution. We are a blip. We are a sudden, anomalous chemical spike in a single layer of rock. Our entire collective works, the Industrial Revolution, the digital age, the sum of our triumphs and failures, will, in the deep future, compress into a layer, perhaps only a few millimeters thick, a strange band of sediment defined by a carbon anomaly, a trace of plastic, and the fossils of the species we pushed into extinction. This is the ultimate lesson in humility. It is a mirror that reflects our own fragility. We tend to operate with an implicit assumption of permanence, that we are the final, stable state of intelligence on this planet. The hypothesis asks, what if we are not? What if intelligence is a recurring experiment, a solution that the planet tries and which then fails? If another civilization could have risen, reached industrial capacity, and then vanished so completely that we cannot even be sure if they existed, then what does that say about our own boasts of permanence? It means that our digital records, our concrete cities, and our global network are not a fortress against time. They are a temporary phase, and the planet's default state is, and always will be, erasure. The true value of this hypothesis is not in finding a predecessor, but in forcing us to confront our legacy. By providing a template for what planetary failure looks like: a rapid chemical spike, a mass extinction, a system thrown out of balance, it gives us an alien, objective perspective on our own time. It allows us to see the Anthropocene through the cold, distant eyes of a future geologist. They will not know our names, our nations, or our gods. They will only see the signal. They will see the thin, dark layer of rock that marks the moment a species briefly gained the power of a geological force, and, in doing so, ended its own story. The Silurian Hypothesis is a thought experiment that has become a warning. It shows us our potential tombstone, and quietly asks us to write a different epitaph. And so, we arrive at a subtle but crucial distinction. The evidence we have examined, the clean record, the false positive of the PETM, leads us to a tentative conclusion. We are, very likely, the first civilization on this planet to have reached a global, industrial scale. We are the first species to have taken the geological step of systematically burning our buried past to fuel our present. The specific, multi-part, chemical fingerprint of heavy industry, the one we so clearly defined, does not appear to have a precedent. But this is where we must be incredibly precise. To say we are the first industrial civilization is not the same as saying we are the first intelligent species. This assumption is the last and most profound layer of our own hubris. We have defined the entire search in our own image. We have equated intelligence with tool-making, with manufacturing, with fossil fuels, and with waste. But what if that is a tragically narrow and self-serving definition? What is intelligence? Is it only the ability to build a circuit board, or is it the ability to solve a complex puzzle, to navigate a three-dimensional social world, to communicate, to feel, perhaps even to dream? If we use this broader, more biological definition, then our planet is not silent. It is, and perhaps has been, for millions of years, alive with other minds, other forms of consciousness. Look at the octopus, a creature that evolved on a completely different branch of the evolutionary tree. It is an invertebrate, more closely related to a snail than to us, yet it demonstrates profound problem-solving abilities. It can open jars, navigate complex mazes, recognize individual humans, and, as many scientists are now beginning to accept, it likely has a form of consciousness, an I, that is alien to our own, yet undeniably present. But the intelligence of an octopus is written in water. It leaves no geological trace. It builds nothing that lasts. Look at cetaceans, like dolphins and whales, with brains larger and, in some areas, more complex than our own. They live in intricate social groups, communicate with complex vocalizations, and pass down cultural knowledge from mother to child, specific hunting techniques, migration routes, and songs that evolve over time. This is intelligence. This is culture, but it is an intelligence that produces no waste, no carbon spike, no technofossils. It, too, is geologically silent. We might be living on a planet that has been a laboratory for consciousness for tens of millions of years, an Earth that has experimented with intelligence in cetaceans, in primates, in corvids, and in cephalopods. We are simply the one experiment that, by evolutionary chance, developed grasping hands and a unique mastery over fire, a combination that led us down the specific, narrow, and loud path of industrialization. The geological record, therefore, is not an objective history of life. It is a biased archive, It only records events. It is deaf to the long, quiet, and perhaps far more common story of being. We can find no evidence of a prior industrial civilization, but we have, and can have, no evidence against the existence of a prior, non-industrial, intelligent one. They could have existed for 1,000,000 years and vanished, leaving behind nothing but bones that we would misclassify as just another animal. This is the true, humbling conclusion. We are not special because we are the only intelligence. We are special, and perhaps uniquely dangerous, because we are the loudest. This is how we must conclude our journey. The Silurian hypothesis is not, in the end, a story about finding intelligent lizards from the past. It is not a fringe search for alien ruins. It is one of the most powerful scientific and philosophical tools we have ever invented. It uses the cold, hard rigor of geology and chemistry to test the very limits of our knowledge. And in doing so, it provides us with something far more valuable than an answer. It gives us a mirror by forcing us to define our own civilization as a testable, physical, geological signal. It strips away all our romance, all our narratives, all our self-importance. It forces us to see ourselves as the planet sees us. A thin, anomalous layer of rock, a chemical event, a sudden, violent spike in the data, defined not by our poetry or our philosophy, but by our carbon, our plastic, and our extinctions. The verdict, so far, is silence. The geological record, when scanned for this specific industrial fingerprint, appears to be clean. This silence does not mean the search is over. It means it has just begun. We now have a new language. We now know what to look for in those smaller, stranger blips in the rock, those unexplained anomalies we once dismissed as noise. But the true takeaway, the one that should settle deep within us, is how the question changes our present. We may be the first to walk this path, but the hypothesis proves that nothing about this path is permanent. It proves that a global civilization can vanish, and that erasure is the default setting of the planet. We are forced to see our assumed permanence as an illusion. The real question the Silurian hypothesis asks is, not were we the first? It is, given the signal of instability we are currently creating, will we be the last? We began this journey by searching the deep past for a distant echo, and, in the end, the only echo we found was our own, a perfect reflection of the chemical signature we are creating right now. By searching for a ghost, we have come face to face with our own legacy, and perhaps, by seeing that legacy written so clearly in the cold language of the rock, we may, for the first time, have a choice about what story that layer will ultimately tell. And so, we arrive at the quiet edge of our exploration, back from the immense depths of geological time. We have searched the rock record, we have weighed the chemical signals, and we have confronted the planet's vast, silent power of erasure. The verdict, for now, is silence. The evidence does not point to a predecessor. There are no clear, unambiguous ghosts in the machine, but the journey has not been in vain. The answer, it seems, was never the true purpose of the question. The purpose was the perspective it gives us. The Silurian hypothesis has failed, so far, to find another. It has given us the ultimate alien perspective, the view of a future geologist looking back at our entire civilization, compressed into a single, thin layer of rock. It has taught us that our permanence is an illusion, that our story is not a separate narrative, but a brief chemical event in the life of the planet. And that is where this conversation truly continues. What do you think? Is our search for a predecessor just a reflection of our own anxieties? Or do you believe there are real ghosts hidden in the rock, waiting to be found? Let me know your thoughts in the comments below. And if this kind of deep, quiet exploration is what you seek, I invite you to subscribe and join us again. For now, in this fleeting moment of the Anthropocene, remember what you are resting upon. 5-billion-year-old archive, an archive that has seen worlds begin and end, that has forgotten more than we will ever know. Let the vastness of that deep, quiet time be a comfort, a reminder that we are just a passing note, but a note that was, for a brief time, aware.